Welcome all. We shall deal now with the material balance calculation, and to understand the material balance calculation we have to know certain transformations that are very essential while doing the material balance calculation. The first transformation that we must need to know is the how to convert weight percent or mass percent. Okay, weight percent, or how to get weight percent or mass percent. Okay, sometimes you may know the mass of a solute, sometimes the total mass of a solution may be, you may know. So if you want to calculate the weight percent or mass percent, then how you would be able to do this? Okay, so there is one simplest formula with the help of which you can convert the mass of a solution finally into the weight percent. Okay, so here weight percent or mass percent is defined as the weight of a solute in 100 gram of a solution. So whenever we want to calculate the weight percent or mass percent, then we have to equate to 100 gram. Okay, 100 gram. Okay, 100 gram of a solution. So here the formula is weight percent is equal to mass of a solute divided by mass of a solution multiplied by 100. Okay, so suppose m is the mass of a solute and m is the mass of the solvent, then the weight percent formula will be like this one. Weight percent is equal to mass of a solute divided by the mass of a solute plus mass of a solvent multiplied by 100. Okay, we will solve a simplest problem over here. The first problem is a solution is prepared by adding 3 gram of a substance A to 17 gram of water. Calculate the mass percent of a solute. Okay, calculate the mass percent of a solute. So we can use the same formula. Okay, the same formula in order to find out the weight percent of a solute. Okay, weight percent of a solute. So here 3 gram of a substance that is given, 17 gram of other substance which is given. So this becomes, okay, 3 gram plus 17 gram, it becomes the total mass of a solution, or we can say, okay, total mass of a solution. And in order to find out a mass of a solute or a mass of a solvent, suppose weight percent of a solute or weight percent of a solvent, then individually we can be able to find it out. Here we will first try to determine the mass of a weight percent of a solute. So we use the same formula over here. Weight percent is equal to mass of a solute divided by mass of a solution multiplied by 100. Okay, so solute, amount of solute, that is 3 gram, divided by total mass of a solution, that is 3 plus 17 which is given, which is multiplied by 100. In order to find out the weight percent of one, we have to multiply it by 100. So what we get is the 15%. Okay, 15%. So by calculation, it's the simplest calculation you can do it, and what you get is the 15% weight percent. Suppose there is no if this equation is not multiplied by 100, then what we would get is the mass fraction. Okay, mass fraction of that particular solute in the stream. Okay, in the stream. Okay, this may be a stream, 3 gram in a 17 gram of water. So this actually can be as a stream, and it can enter into the process unit. Okay, so the stream consists of 3 gram and 17 gram of water, suppose. Okay, so this stream, in this stream, how much is the mole mass mass fraction of one of the constituent, you can easily determine. Similarly, if you want to convert this mass fraction into weight percent, okay, weight percent, then in that case also you have to just multiply it by 100, so that mass fraction is multiplied by 100. Then what you would get is the weight percent or a mass percent. So this is the easiest conversation that we require, or we often require, whenever we are solving, or whenever we want to solve a material balance calculations. Okay, so it is essential for us to know how a different conversations that are required and is necessary for us to understand. Now the next problem, okay, here is the calculate the mole fraction of HCl and H2O in a solution of HCl acid in water containing 20% HCl by weight. Okay, so what we are asked to determine is the mole fraction of HCl and water. Okay, mole fraction of HCl and water. So this HCl and H2O together make a acid solution. Okay, it's a acid solution. Okay, so initially what is given, the 20% HCl is already present in the solution. Okay, 20% acid is present in the solution. So what we require to calculate first is the moles. Okay, so moles is equal to mass divided by molar mass. So here is the solution. So this formula as we required, because moles is nothing but a mass divided by molar mass. So here no value is given, only what is given to us is the 20% HCl. Okay, 20% HCl by weight. So here you can calculate that the solution may be containing 80 gram. Okay, 80 gram of water. Okay, 80 gram of water or 80% of water. The remaining part is the water. Okay, so 80% water, 20% HCl. So these two together make a solution, HCl solution. Okay, acidic solution. But this acidic solution actually contains 20% HCl. That means 20 gram of HCl is dissolved in 80 gram of water. Okay, so this is actually a given in the problem. The solution contains 20 gram of HCl acid and 80 gram of water. And you know that the molecular weight of water as well as HCl is 36.5 gram per mole is the molar mass of HCl, and molar mass of water is 18 gram. So just put these values in the given formula. You can calculate, or we can calculate the moles of that particular constituent making the solution. Here HCl, for HCl this comes out to be 0.547 moles of HCl, while for moles of for water it comes out to be 4.44 moles of water. Now what is asked in the problem? Calculate the mole fraction of HCl and H2O separately. Okay, we have to calculate the mole fraction of HCl and H2O. So we know we have got the moles of HCl as well as H2O. Okay, that is making this this stream or this acidic solution. So mole fraction can be easily calculated. Mole fraction of HCl, which is equals to, okay, mole fraction of HCl or mole fraction of solute. This formula you can use, mole fraction of solute, which is equal to number of moles of solute. Okay, number of moles of solute. Okay, moles of solute divided by the total moles of that HCl as well as water. So number of moles of solute plus number of moles of solvent. So the moles of solute, okay, moles of solute, that is moles of HCl here is 0.547, and this is the total mole. It comes out to be 0.109 as mole fraction of HCl. Similarly, you can calculate the mole fraction of water also. Okay, so mole fraction of water, in order to calculate the mole fraction of water, the moles of water given or calculated is 4.4 and which is divided by the total moles, that is moles of HCl as well as moles of water. This two together comes in the denominator, and when you calculate, what we get is the 0.891 mole fractions of water. Okay, mole fraction of water. So in this way it is possible you can convert the percent solution into mole fraction or mole fraction into percent solution. So you must be in a position to interrelate or convert each of the given terms. Okay, each of the given term as per the convenience. Okay, because in the problem it may be given, suppose two streams. Okay, the two streams are entering into the any unit process. Okay, so and the unit of each of the stream, okay, unit of each of the stream, that is the unit or quantity unit is given in different way. Suppose one stream is expressed as moles, and other stream is expressed in kilograms, suppose. Then you must be able to convert the streams in one equivalent unit. Okay, so that the calculations can be done easily, or we can say that we could be in a position that the calculations can be done on the stream. Overall calculations can be done if the unit are same. Okay, the unit must have to be same, and therefore it is necessary that whatever the stream, whatever the unit that the stream may have and entering into the unit process, we should be in a position that we should be in a position to convert all that stream into one unit, so that the further calculation becomes easy. Otherwise you wouldn't be able to make the calculations if the streams are expressed in different unit. Okay, so unit should be homogeneous, or unit should be unit should be the same whenever we want to perform the calculations. So in a while performing the material balance calculation, it is necessary that unit that is mentioned or expressed of different stream should be same. So when this happens, then and then only we can be able to perform the material balance calculation, otherwise no. Now the next problem we will solve here is conversions. Conversion using mass and mole fraction. Okay, conversion using mass and mole fraction. So the problem is given over here. A solution contains 15% A by mass. Okay, 15% A by mass. So its mass fraction is given as XA is equal to 0.15, and other constituent which is 20 more percent. Okay, 20 more percent B, other constituent B is there, whose what unit is given as mole percent. Okay, mole percent B. Okay, this is given in mole percent, and this is given in mass fraction. Okay, this is given in mass. Okay, percent as well as mass fraction, and other constituent is expressed as mole percent. Okay, mole percent, 20 mole percent, or this is mole fraction. Okay, this is mole fraction. Okay, so what is asked? Calculate the mass of A in 200 kg of the solution. Okay, 200 kg of the solution. So we have been asked to find out what is the mass of A in 200 kg of a solution. Okay, 200 kg of a solution, mass of A. Okay, not the mass of B. It has been asked to us to find out the mass of A in 200 kg of a solution. So what formula we can use? Mass fraction is equal to mass component divided by the total mass. You know that mass fraction is given. Okay, mass fraction is given, and total mass of A. Okay, mass of A in 200 kg. That means 200 kg is the total mass. Okay, 200 kg is the total mass of the stream. Okay, that is entering in the unit process. So 200 kg is the total mass, and how many moles, or what is the mass of the constituent A present in the 200 kg of the solution? Okay, 200 kg of the solution. That is what is asked in the problem. Okay, that is what it is asking the problem. So what is unknown? The mass component I. Okay, the mass component, that is the mass of A, is unknown. Mass fraction, of course, it is given. It is 0.15. In terms of mass fraction, it is 0.15. In terms of percentage, it is 15%. Mass percent or mass fraction. Okay, it is 15% mass percent, and 0.15 as mass fraction. So mass fraction is equal to mass component divided by total mass. So you can use both the formulas, weight percent formula or mass percent formula, or mass fraction formula or weight percent formula. So we are here using the mass fraction formula in order to find out the amount of that particular constituent A present in the 200 kg of a solution. So here XA, that is mass fraction, is given as 0.15, mass component that is to be find out, and total mass is 200 kg. Okay, so put this in the equation, 200 kg and mass fraction as 0.15, just cross multiply. Okay, just cross multiply. What you would get is the mass component I, which comes out to be 30 gram. Okay, which comes out to be 30 gram. Okay, here 200 kg of total mass multiplied by mass fraction, which is 0.15 kg of A, in kg of solution. Okay, kg of solution. So in 1 kg, suppose this is 0.15. Okay, this in 1 kg, this is 0.15. So how much is in the 2 kg? Likewise, you can make the calculations here. Okay, so all units are expressed over here. So whenever you make the material balance calculation, all unit and the quantity must have to be expressed. Okay, so 200 kg of solution, total mass. Okay, in that the mass fraction of A is 0.15 kg okay, kg of A, and the answer comes out to be 30 kg of A. That is, the 30 kg of A is one of the component, that is A, present in 200 kg of the solution. Okay, 200 kg of a solution contains 30 kg of A constituent. Okay, so mass fraction formula or mass fraction formula or mass percent formula also can be used to find out the amount of A in the total quantity, amount of one of the constituent in total quantity, provided we should know either mass percent or its mass fraction. Okay, mass fraction. Even when we know the mole fraction also, we could be able to calculate, or we could be able to find out the amount of that particular constituent in a solution. Now next problem is, a solution contains 15% A by mass. Okay, 15% A by mass given as XA, that is the mass fraction. Okay, mass fraction of the constituent A is given. Okay, and 20 mole percent B, that is the mole percent of constituent B is given. What is been asked? It has been asked that to calculate the molar flow rate of B. Okay, molar flow rate of B. Okay, molar flow rate of B. It is not asked for. It is not asked to calculate A. Okay, it is asked. It has been asked to us to find out the molar flow rate of B in 1000 moles solution per minute stream. Okay, the stream is moving into the unit process at a rate of 1000 moles per minute. Okay, 1000 moles per minute. It is coming into this unit process. Then what we have to find out is the molar flow rate of B in 1000 moles of moles solution that is entering per minute in a unit process. Okay, so here it is not required, so what we require is the 20 mole percent B. Okay, 20 mole percent is given. Okay, mole percent is given over here. Similarly, simultaneously it has been given to us the fraction of that mole per mole. Okay, mole fraction is also given. Okay, 20 mole percent. So in mole percent, in terms of fraction, it would be 0.20. So they are interchangeable. Okay, you easily can interchange, and we have seen it in the earlier lecture, in the earlier slides, that these are interchangeable. Okay, these are actually interchangeable. Okay, so either you can use this to calculate the molar flow rate of B, or you can use mole fraction to calculate the molar flow rate of B in 1000 moles of solution. So what is the formula? So here what we are using is the mole fraction. Okay, mole fraction, that is the fraction formula. Okay, this formula, mole percent, we are not using here mole percent formula. We are using the mole fraction formula in order to find out the amount of B in 1000 moles of solution. So mole fraction is equal to mole component of the constituent divided by total moles. Okay, divided by total moles. So here total moles. Okay, total moles is 100. Okay, total moles is 1000. Total moles is 1000. We don't know what is the moles of B in total moles. Okay, what is the moles of B in total moles of a solution? Okay, total moles of a solution. We just want to find out this as this in terms of mole. Its fraction is given. Okay, its fraction is given. Mole fraction is given. Okay, its mole fraction is given, and it is 0.20. Okay, 0.20. So 0.20 is the mole fraction. Moles of component, that is B, is not given. Mole component of B, that is not given, but total moles is given, that is 1000 mole. 1000 mole. So put all this value in this equation. Okay, similarly you can be able to calculate the amount of, okay, or the moles of, okay, moles of B in 1000 moles of solution. This comes out to be 200 moles of B is present in 1000 moles of solution, and it is also moving with the same rate, or it is also coming into the reactor, or we can say in a process at the same rate as the total solution coming into the process. Okay, so it is 200 moles of B is present in 1000 moles of solution. That means remaining portion, okay, remaining 800 moles of solution may be suppose water or any other constituent, I must say. Okay, so the amount of this particular constituent is 200 moles of B present in 1000 moles of solution. Now the next one, a solution contains 15% A by mass. Okay, 15% A by mass. Its mole fraction, sorry, mass fraction is given. Percentage here means it's a mass fraction. Okay, percentage of A by mass. So it is a mass fraction. Okay, it's a mass fraction. And 20 mole percent B. So mole percent. Okay, this is a mole percent. Mole percent of B is given, and this is a mole fraction of B. So this is a mole fraction of B. Okay, what is been asked to find out? Calculate the total solution flow rate. Calculate the total solution flow rate that corresponds to a molar flow rate of 25 kg moles of B per second. So what is been asked? Total solution flow rate. Okay, total solution flow rate has been asked. This total solution flow rate or the total solution would carry 25 kg moles of B. Okay, 25 kg moles of B. So something different what we have learned so far is been asked in this problem. Okay, so you can use the same formula, since either you can use the percent formula or a fraction formula. Okay, here mass fraction or mass percent, here mole percent or mole fraction. So we are here using mole fraction because it has been asked in our problem to find out the total solution flow rate that corresponds to or that contains 25 kg moles of B. Okay, that contains 25 kg moles of B. So in terms of B or the constituent B, in relation with the B constituent B has been asked in the problem, and that is why these things that is given in our problem is not at all necessary for us to do calculations. So we should focus more on mole percent of B and its mole percent of B and its mole fraction. So here that is why we are using the same formula, mole fraction, which is equal to moles component of that particular constituent B divided by total moles. So here in this case, here in this problem, mole fraction we know that is 0.20. Total moles we want to find out. Okay, calculate total solution flow rate. Okay, calculate the total solution flow rate correspond to a molar flow rate. Okay, correspond to a molar flow rate. Okay, this is moving or this constituent is present in terms of mole. Okay, in terms of mole, or its value is given in terms of mole. Okay, its value is given in terms of mole, and that is why the moles of total moles of the solution that is moving or flowing or having a flow rate is to be determined. So here total moles is unknown to us. Total moles is unknown to us. Mole component of constituent B in a total solution flow rate is 25 kg moles, and therefore this numerator we know, mole fraction we know. So what is to determine is the total moles. So put all this value in the equation. What you would get, that is this total moles comes out to be equal to 125. Okay, 125. Here you can see the total moles that comes out to be 125 kg moles. Okay, kg moles. Okay, kg moles, same unit we apply over here. Kg moles solution that is moving per second, or the flow rate is 125 kg moles solution per second, or the solution is moving with a concentration, with a quantity what we call 125 kg moles solution is moving per second. Okay, moving per second in suppose any unit process.